transformation. So without wasting the time, let us start Laplace transformation. We have given the function f of t, where t is non-negative variable, t greater than or equal to 0. This is non-negative nature and time is also non-negative. So that's why we are using the parameter t for the time. So we have given any function f of t, only the condition is t must be non-negative. Then the Laplace transform of the given function is defined by this integral, integration e raised to minus stf of t dt, where it is from 0 to infinity. So here this integration e raised to minus st into f of t should be existed. If this integration does not exist, then we can say that Laplace transform does not exist. So there must be condition under or for which kind of function f of t the integration exists. So in the next lecture we shall discuss few functions for which Laplace transformation does not exist. Today our concentration will be on those functions for which the Laplace transform we have. The symbol for Laplace transformation is either capital L of f of t, or it is capital F of variable s, or it is f bar s. Why we have the variable s here? Because we are going to integrate with respect to t. So we substitute the limit t equal to infinity and t equal to 0. So the remaining quantity will be in terms of s. So this quantity represents the function in terms of s. So we have the function of variable s, which is defined by integration over 0 to infinity e raised to minus st into f of t dt. So the definition is very simple. If we have given any function f of t, then we try to integrate this integral, and the final answer will be called the Laplace transformation of the said function. So let us discuss the example we have given. Let us start with very simple function. This is the constant function f of t equal to 1. Obviously t is from 0 to infinity, so this condition we have t greater than or equal to 0. The curve f of t equal to 1, t is the domain, so we have domain axis. F of t will be the codomain. This is the function, so here we have the values of function, and here for all t function is constant, it has value 1, so this is f of t equal to 1. So this is the curve we have given, and we are going to apply, or we are going to find the Laplace transformation of this function. We know the definition of Laplace transform. Laplace transformation of f of t is 0 to infinity e raised to minus st ft. What is ft here? Here f of t is 1, which I mentioned here from with red color, so that easily we can understand that we are going to substitute the value of function f of t equal to 1 into e raised to minus st is e raised to minus st. So we integrate this quantity. We know that the integration of e raised to ax is e raised to ax divided by a. So here constant is minus s, so the integration is e raised to minus st upon minus s, and this is the limit from t is equal to 0 to infinity. So let us take minus 1 upon s common. Then we have e raised to minus st from 0 to infinity. We substitute t equal to infinity. So s into infinity is infinity. This is e raised to minus infinity. When t is equal to 0, this is e raised to 0. So what we have? Minus 1 upon s, e raised to minus infinity, which is 0, that we know, minus e raised to 0 is 1. So this is 0 minus 1 is minus 1, and therefore the quantity will be minus minus plus 1 upon s. So what we have? Laplace transform of 1 is 1 upon s. This is one of the important formula for Laplace transformation, which we memorize for this semester. The curve, this is the function of variable s. So we have the domain s, and this is the function capital F of s, and the curve is 1 upon s. So what does it mean? We have given this function f of t equal to 1, which is converted into this function 1 upon s after apply the definition of Laplace transformation. So the Laplace transformation of this curve is this curve simply. We have another example. Now in place of the constants, we choose the linear function. Here it is f of t is equal to t. So the curve f of t equal to t is this. Now let us try to find the Laplace transformation of this curve. Again, the same thing we applied, which we applied in the last example. We have the definition of Laplace transformation. Laplace of f of t is this. We substitute f of t equal to t, which is this. So this is t into e raised to minus st dt over 0 to infinity. Now the question is, how do we integrate this quantity? So we assume t is as u and v as e raised to minus t, and we apply the integration by parts. Now onwards, we shall try to apply the general rule of integration by parts. So let us see. We integrate this function, u as it is, and then we integrate e raised to minus st with respect to t. So it will be e raised to minus st upon minus s. Opposite sign, we have this opposite sign is this. We have started with positive, then its opposite is negative. Now we differentiate this function. So the derivative of t is 1. We again differentiate, we again integrate this quantity with respect to t. So it will be e raised to minus st upon minus s, again divided by minus s. So what I did here, the blue colored represent the differentiability and red color indicates the integrability. Now again, if I differentiate this quantity, then it will be 0 and integration of this, but 0 into anything will be 0. So we stop here, t equal to 0 to infinity. So the integration of this quantity will be this. Now we substitute t equal to infinity. So let us start with t equal to infinity. So this is only the simplification of this thing with the simple terminology minus t upon s e raised to minus st. E raised to minus st is 1 upon e raised to st. So I wrote here in the denominator. This will be minus minus plus. So minus e raised to minus st upon s square this is. Now let us substitute infinity here. So what happened when we take infinitive? Then this is infinitive upon e raised to infinitive. E raised to infinitive is infinitive. So this is infinitive upon infinitive form, right? And we know that how do we deal with infinity upon infinity? It is indeterminate form. So we are supposed to apply L'Hopital's rule to evaluate this quantity when t is equal to infinity. I am not going to apply right now. Let us write answer direct. So when t is equal to infinity, this term has value 0. Again, when t is equal to infinity, this is e raised to minus infinity, which is 0. So we have 0 minus 0. This minus sign I specially indicated by red color. This minus sign for the lower limit. We are going to substitute t equal to 0 now. So when t equal to 0, 0 into this is 0, and t equal to 0 here. So this is minus 1 upon s square. So the final answer will be minus minus plus 1 upon s square. So the Laplace transform of t is 1 upon s square. This is the function of variable s, right? So let us try to plot the curve. So this is the curve of 1 upon s square. So the curve t is converted into this curve under this transformation. Now the next example, we have given the function f of t is equal to t square. The same conditions we have, t greater than or equal to 0 for all the examples. This is the condition we have. So the function f of t equal to t square. Now we are not going to plot each curve, right? That you can plot using any mathematical applications. You may use mobile applications, as well as you may use your computer also. These are only two-dimensional curves, so we don't require much graphics. Laplace transform f of t is this. F of t is t square, so t square into e raised to minus st dt. Now here what happened? T square into e raised to minus s. If we apply our usual rule of integration by parts, then we have to apply 2 times. But if we apply the general rule of integration by parts, then we will evaluate this quantity just in a single step. So again, the same logic we have. T square will be assumed by u, and v is e raised to minus st. So what is the first step of the rule? U will be as it is, and integration of v. So integration will be with red color, and the differentiability will be with blue color. We always apply opposite sign nature between two terms. So here we have positive sign, then we must have negative sign now. The derivative of t square is 2t. Integration of this quantity is this. Here we have minus sign. So again, opposite sign will be plus. The derivative of 2t with respect to t. Keep in mind, everything is differentiable and integrable with respect to t only. So the derivative of 2t is 2, and the integration of this quantity will be e raised to minus st upon minus s cube. Again, we have minus sign here, and the derivative of 2 will be 0, and integration of this, but 0 into integration of this will be 0. So we stop at this stage, and we have the quantity over t equal to 0 to infinity. So first we apply t equal to infinity, then again the same situation we have. This is t square divided by e raised to st. Infinity upon infinity quantity we have 2t upon e raised to st, infinity upon infinity quantity. So for these two terms we apply L'Hopital's rule. So for these two terms the answer is 0. E raised to minus infinity is also 0, that you know. So I mean now you can apply, you are able to apply the limit at infinity and at 0. So let me go direct to the answer. Laplace transform of t square is the final answer is 2 upon s cube. So three important functions we have. Laplace transform of 1 is 1 upon s, Laplace transform of t is 1 upon s square, and Laplace transform of t square is 2 upon s cube. One more example we have. Now let us choose the exponential function. We have given e raised to at, where t is our usual time variable and a is any real number. So the Laplace transform of e raised to at is this. E raised to minus at into the function f of t will be e raised to at now. Right. So here this is the quantity. See, the base of these two quantity are exponential. They are same. So we just add these two quantity, minus st plus at. This is we took t common here, so it is minus s plus a into t. Again we take minus sign common. Integration 0 to infinity e raised to minus of s minus a into t. So now let us integrate this quantity with respect to t. So it will be e raised to minus s minus a upon the constant, which is minus of s minus a. We substitute 0 to infinity. When t is equal to infinity, now we know e raised to minus infinity is 0. So at upper limit this is 0. At lower limit the quantity is 1. So the Laplace transform of e raised to at is 1 upon s minus a. Now one thing I want to mention here. When we substitute t equal to infinity, I told you that this is e raised to minus infinity. Why this is e raised to minus infinity? Or is it true that this is always e raised to minus infinity? S is variable, a is the constant. So suppose a equal to 1 and s is equal to 2, right? Then this is minus t. Suppose a equal to 3 and s equal to 1. So 1 minus 3 is minus 2, minus 2 into this minus. So this is minus minus plus. Then this is e raised to 2t. Right. So I mean when s minus a is greater than 0, then only this quantity will be minus infinity. Right. So this integral exists only if s is greater than a. Right. So under this condition, if s is greater than a, then only Laplace transform of e raised to at exists. When s less than or equal to a, that time the Laplace transform of this function does not exist. What happens if a is equal to 0? When a is equal to 0, e raised to 0 is 1. And we know that Laplace transform of 1 is 1 upon s. So when s is only less than a, then Laplace transform does not exist. S equal to a is very much obvious case that we know, and for s greater than a, Laplace transform of e raised to 8 is 1 upon s minus a. We have one more example. Okay, so what we are doing, first we choose constants, then we choose polynomial t square, t cube, t raised to 4, right? Then we choose exponential function. Now we are coming to trigonometric functions, sine, cos, sine hyperbolic, hyperbolic trigonometric functions also we have. So sine hyperbolic, cos hyperbolic, tan hyperbolic, right? So here we have given a very simple trigonometric function sine 80. Okay, what happen if we apply the definition of Laplace transformation? It will be e raised to minus st into sine 80. Do you know how do we integrate the quantity? For example, here if I write sine 80, then sine 80 into e raised to minus st, then this integration is possible, but it takes some time, right? So do we have any other option? We know the relation between sine function and exponential function. We know the Laplace transformation of exponential functions, right? So the relation is this: sine 80 is e raised to I80 minus e raised to minus I80 divided by 2i. Let us apply Laplace transform both sides. So we have Laplace of sine 80 is Laplace transformation of this quantity. Actually I forgot to write I here. So just consider the denominator as 2i. 1 upon 2i is the constant quantity. We take it outside. Then the Laplace transform of these two functions is Laplace of e raised to I80 minus Laplace of e raised to minus I80. So this 1 upon 2 we have. Now e raised to I80. What is the Laplace transform of e raised to 80? It is 1 upon s minus a. Here the constant is ia. So the Laplace transform is 1 upon s minus ia. Here the constant in place of a I have given minus ia. So the Laplace transformation is 1 upon s minus ia. Right. So this is 1 upon s minus ia and this is 1 upon s plus ia. Please consider here 1 upon 2i. So this is here also it is 1 upon 2i. Now let us take LCM for more simplified. So this is s plus I into 1 minus of this thing. So it is s plus ia minus of s minus I divided by product of these two quantities s minus I into s plus I, and this is 1 upon 2i actually. So here s and s will be cancelled out. This is minus minus plus, so 2 times ia. So these 2 and 2 will be cancelled out. In the denominator we have also I, so I will be cancelled out. Then it gives us a upon s square plus s square. So the Laplace transformation of sine 80 is a upon s square plus s square. Now can you find the Laplace transformation of cos 80? What is the relation between cos function and exponential function? It is cos at is e raised to iat plus e raised to minus iat divided by 2. Keep in mind here it is 2 only. In the denominator we don't have 2y in the formula of cos. So there is no mistake in this formula. Please make sure. So what will be the Laplace transformation of cos at? It is in homework. Same way, now we have given the relation with hyperbolic trigonometric function with exponential functions. Cos hyperbolic at is e raised to at plus e raised to minus at divided by 2. Sin hyperbolic at is e raised to at minus e raised to minus at divided by 2. So the logic of all these three functions are same. We take 1 upon 2 common. We apply addition rule. This is Laplace transform of e raised to iat plus Laplace transformation of e raised to minus iat. For the last example, Laplace transform of e raised to at minus Laplace transformation of e raised to minus at. Then we apply the formula of Laplace transformation of e raised to at everywhere for all these 6 functions. Right. Then we take LCM and we simplify. So for all these functions the answer should be in this format. You people just try to work out this Laplace transformation of these 3 functions: cos at, cos hyperbolic at and sin hyperbolic at. Again we shall meet on Monday. So in Monday we shall recall today's session, the important formulae: Laplace transformation of 1 t square. In general we have t raised to n. You just try to work out for t raised to n. Otherwise in the next session we shall look at the Laplace transformation of t raised to n with the relation with gamma function. Then we have exponential function, trigonometric functions, sin at, cos hyperbolic at and sin hyperbolic at. We shall meet on Monday. Actually, do you know what I'm missing? I'm missing your faces. Continuously, I'm watching only on the screen. Right, I don't have the faces, some tired faces, some smiley faces, and a few students may took rest on the last benches. All such things I'm missing. I really miss you all, guys. Please take care. Take care of your health. Take care of your family. Tomorrow is Sunday, and all we know what we have to do tomorrow. Right, please don't be outside of your home. Please stay home, be safe. Again we shall meet on Monday. Thank you.